Okay, so let's look at another solid that we got to go find the volume of. So they're giving us two equations here, and this is where students get a little tricked out. They're like, oh my goodness, which one of those is the capping surface? I'm confused. Well, you want to do a lot of these problems to get practice so that you can distinguish who's the capping surface and what's contributing to the region of integration. And if you can't decide, then you need more practice, okay?
Wouldn't your capping surface just be the second equation?
Well,
If you put in y equals, well, y equals form?
well, traditionally your capping surface is going to be a function of x and y. So it's going to be like a z kind of thing.
Okay.
So in this particular problem, this right here is your capping surface. Because you can replace the z, I could rewrite that equation as fxy equals x squared plus y squared plus 1. Because remember, z means the same as f of xy.
Right.
And then this has nothing to do with the capping surface, believe it or not. It has to do with the region of integration that's flat in the xy plane. It does
okay.
have to do with one of the sides of your solid. So, what I'm going to try to do here, just for kicks and giggles, to help you visualize this surface a little, the capping surface and all this good stuff, a little bit better. I'll go into GeoGebra and we'll graph. Both of these are surfaces. The second equation is actually the equation of a plane that's parallel to the z-axis because it doesn't have a z in it. Okay, so it's going to be one of the sort of the sides, but it won't be the capping surface.
Because that's what it looks like, for example, 11. Or cap, just like you just
yeah,
said.
that was a plane, but remember that particular problem had a z in it, didn't it?
Right. It didn't give us
So
the
what we
secondary
did is
equation.
we solved it for z. If you read your notes there, we solved it for z in order to get it to be the capping surface.
I see that now.
So folks, do you see this is the capping surface? Now, everybody's looking at this paraboloid. We're not finding the volume of that paraboloid. No, 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 no. The underbelly of it, the underbelly of this paraboloid is going to be the ceiling for our solid. Because let's read the problem again very carefully. A lot of students don't read the problem very carefully and then they blow it. And then I take all their credit away because they're seriously misguided. Do you see that they're telling you the first octant? Please circle that on your lecture notes. And I mean, put stars by it. Because that's telling you that in 3D here, this solid that we're trying to find the volume of, we're going to restrict the portion of the solid that lives here in the first octant when x is positive, y is positive, and z is positive. So it's bounded by the 3 coordinate planes when you're in the first octant. So like the bottom of the solid is going to be bounded below by the xy plane. One of the sides of the solid is going to be bounded by this xz plane. And then another side of the solid will be bounded by the YZ plane. Those 3 coordinate planes are going to be sides of the solid because we're only going to consider that even if the solid is, extended beyond the first octant, we're just going to find the portion of the solid's volume that's in the first octant because they told us to. Now, they don't always tell you that, so be on the lookout. Sometimes they may say first octant or bounded by the coordinate planes, and sometimes they don't. And if they don't, then you can't assume this. The volume is for like all over, whatever it might, overlap in all sorts of other octants. So back to the GeoGebra picture. Now, what about that plane? The plane, which has the equation 2x plus y equals 2, do you notice it's parallel to the z-axis? Can everybody see that? So it's not the capping surface. That bluish greenish plane there is going to be one of the sides of your solid. Now it looks here like the first octant is located in the back side here. I don't know how to rotate this a little bit. I can rotate it now a little bit. Yeah, come on, rotate now. Oh, I have to look at this a little bit more on how to rotate. Is this rotate? No, that's an undo. Okay, so the underbelly is the ceiling, and then on flat here in the XY plane is going to be the base of the solid. Okay, so back to your lecture notes so you can sort of see what's going on here. What I'm saying is, and I know this is tough to visualize, and you don't have to, oops, can you guys still hear me?
Yes.
Okay, for some reason my cooling thing went off. I don't know why. Oh, that's weird. Don't know. Very strange. Okay. So if I were to draw a picture of this solid, I don't usually ask you to draw every single solid that you're going to find the volume of. But if you can kind of get a visual on it, it doesn't hurt. You definitely want to draw the base of the solid, whether or not they ask you to, okay? So if I were to draw this solid, knowing what I know now, here in the XY plane, we're in the first octant. This plane that we saw was vertical. If you solve it for y, you'll get y equals 2 minus 2x. And so if you graph the trace of the plane as it cuts through the xy plane here, if you graph 2 minus 2x, it's going to be a line that has a y-intercept of 2, and then I believe the x-intercept is 1. And so I'll stick to the first quadrant, and then I claim that, hey, Nick S., can I meet with you after class?
Yeah.
Okay. I was hoping to see you today, but I didn't see you. We still got to talk. Okay. So this, folks, is the base of the solid. Right there. It's a little triangular thingy-dingy. And so if I draw the base of the solid here in 3D, it's that triangle there. And the underbelly of the paraboloid is the ceiling. So that's not part of the solid, but so the capping surface, if you're going to it's sort of this curvy thing. So the solid that we're trying to find the volume of looks like this. Can you guys kind of picture this with a sort of concave top? That's the solid we're trying to find the volume of. Pretty weird, huh?
Yeah.
So now the question is, can we set up the double integral representing volume? So volume is going to be the double integral over the region, and the region R is this, the base of the solid. We just drew it, okay? So over that region R, we're going to put the capping surface here in the integrand, and then dA is the shorthand for the area element, which is either dy dx or dx dy, depending on your choice for the order of integration. So this is key right here. Now, we can't evaluate this integral yet because it's sort of in generic form. We have to iterate the double integral. Iterate. What does that mean? That means put the limits on there and don't guess. Well, how do you do that? You look at the sketch of your region of integration, in this case, to help you iterate the double integral. And my favorite choice of integration, if I can get it, is the vertically simple one, which is the order dy dx. Dx dy is most of the time trickier because you have to think in terms of functions of y instead of functions of x. I'm just saying, you know, it's up to you, because I claim this region, this little triangular base, is the type of region that can be considered either vertically simple or horizontally simple. Your choice. So you want to pick the choice that you feel it's easier for you. Okay. So I always think it's easier to do dy dx. I'm just saying. Now let's iterate. So let's do the outermost limits first, because those always have to be pure numbers. So what pure number to what pure number is happening here on this little sliver for what x is doing on that region?
0 to 1.
Really, that's exactly right. 0 to 1. Boom. Okay, we're halfway done with iterating. Now the harder part. Y, don't go 0 to 2 here. No. Well, look,
Okay.
Y is going from 0 to 2. Yeah, but if you put a representative rectangle in here, and then you can slide that representative rectangle to the left or the right, and I like to use my little man instead. That's my representative rectangle. Here's my little man.
Y equals 2 negative or 2 minus 2x.
Is that the upper or the lower limit?
That's the upper limit.
Very good. And then the lower limit, what's his feet resting on?
0.
Mm-hmm. So there you go. Now remember, I give partial credit if you can set up the correct double integral, because I'm so happy you did that part. It's like, yay, the setup, because sometimes that can be tricky. Now go integrate it. This is not a hard integral to integrate because it's just a polynomial you're integrating. You know, you don't have to use like the arctan rule or, you know, exponential rule. So if I'm just integrating this with respect to y first, because that's the inner integral, you're going to hold x constant. So you'll have x squared y plus y cubed over 3 plus y. And then I'm going to evaluate this between the limits of 0 up to 2 minus 2x. Okay. And then I still have an outermost integral, so please continue to write that. So everybody knows you're not going to be done. I'm just going to put that in there just to remind myself. And then I'm going to evaluate at the upper limit first. So everywhere I see a y, I'm going to plug in the 2 minus 2x. And then after that, I'll plug in a 0. And for this particular expression, 0 evaluated is going to go to 0. So I don't have to worry too much. Now, this is going to be a little bit of a hot mess to integrate by hand, as you can see, because you've got a lot of polynomial action here. That is a Calc 1 integral at that point. I mean, it's not something you guys are not capable of doing, certainly, but the question is, how do you want to do it? So there's some options. What's one option? Well, multiply everything out, expand and multiply, and have one big old polynomial, and then collect like terms, and then go for it. And what I do is I do part of that. But this particular term, I don't feel like expanding that out and multiplying because, you know, 2 minus 2x cubed is a little bit tedious to multiply out, but you could. But I'm going to do u sub on this instead with the power rule. But everything else I'm going to collect. So I'm going to distribute this x squared over here and then add it to the 2 minus 2x over here. And so those guys end up being, after I've collected like terms, 2x squared minus 2x cubed plus 2 minus 2x. And then I have that other term that I don't feel like doing all the work for, you know. Now, of course, at this point, you could just bail out and go, I'm just going to use my calculator, you know, which is able to do definite integrals of, you know, with functions of a single variable. So you could just, you know, if you're lazy, but I want to see the work done by hand on your quiz. So for here, I'm just going to say, et cetera, et cetera. You go figure out and do this by hand. And the final answer for this problem is 11/6 cubic units. And make sure that when you're doing a volume double integral, you do get a positive result. I get students who like, oh, well, I got negative 11/6. Well, okay, it's cool. It's like, yeah, but remember, this was supposed to represent a volume, and like, we don't want to have negative volumes. Okay, questions?
Did you know that if the plane 2x plus y equals 2 was going to be the base or the region of integration?
It's going to contribute to the base. It isn't the base itself.
Yeah, because I was almost tempted to look at that surface and like get the xy trace, like set z equal to 0.
Exactly. That's what you would do. You would set z equal to 0. Oh, you mean in the for the capping surface?
Yeah, correct. Yeah.
Well, the problem if you did that, and I think I'm talking to George. Is that correct, George?
Yes.
Okay, if you set z equal to 0 for this one, it wouldn't work like it would for the previous example, because the previous example we did last time, the capping surface, which was a plane, that's this problem here. Do you see how that capping surface actually cut through the xy plane right there, that trace? Can you see my screen?
Yeah, I see it.
So when you set z equal to 0, that was legit and okay because that particular capping surface actually intersects with the xy plane. However, it's not going to work for you here because I claim you will get no solutions. Well, why
The
is that?
surface was above the XY plane. It's not
Yes,
even.
sir. Yes, we saw from the GeoGebra graph here. I hope you see this cute little paraboloid. You see it never touches the XY plane.
Mm-hmm.
So if you would try and set z equal to 0 there, there are no solutions to that because there are no XY plane intersections there or traces. Does that help?
Okay. Yes, it helps. Thank you.
Okay. So you have to be careful. Sometimes your capping surface might cut through and help actually contribute to your region of integration in the XY plane. This example has a completely different flavor because the capping surface never intersects with the XY plane. And it's just sort of hovering above the XY plane. And that's why I put this in my lecture notes, just to distinguish it from the other example. So I wanted you to see everything. Okay, new example now. Oh yeah, I'm giving you a new flavor. Let's see. Keep your eyes open as to what's different about example 13 when we compare it to examples 11 and 12. I'll give you a hint. It's harder. What makes it harder? Ah! Oh, let's just pretend we don't know yet. All right. So first, sketch the region of integration. Well, I don't know. They didn't give me enough information. Well, yeah, they did. They told you that you're in the first octant, so that helps. So you know you're bounded by the coordinate planes. Anything else? Sure, they gave you a whole set of equations here, so go graph them. So x equals 0 in 3D is actually a plane. It's a plane, okay, that is basically, I mean, we could go to GeoGebra here and graph it. What the heck? Let me just show you. Like if we go down here. Oh, where? We get one of these puppies. Ah, here we go. X. Where's my symbols? I don't see it. Equals 0. Hit it. Is it going to graph it for me? No, it's thinking it's not. Oh, it's graphing it on a number line. Oh, man, those pooper heads. They're just, see, this is one reason why I don't like GeoGebra as much as my other. So that's funny. Okay, so if I were to graph x equals 0, let me just show you if you were to graph it in 3D. Oh my goodness. Here in 3D, if you're going to graph x equals 0, good Lord. First of all, what does x equals 0 look like in 2D? You guys all know how to do that because that's like a pre-calc or a beginning algebra problem, right? Isn't it just the y-axis line?
Yeah.
Okay, vertical line, everybody very cool with that? So if you graph that, do you guys remember cylindrical surfaces? So here's the y-axis in 3D. And then I'm going to whoosh this up. So that is the plane x equals 0. So that's just going to just serve as one of the sides of my solid because it's basically the YZ coordinate plane. Okay, so this is a plane. In fact, it's the entire YZ coordinate plane standing up vertically, but it's going to operate as one of the sides of our volumes of our solid and not the capping surface, for sure not the capping surface. We already know what the capping surface is. I hope everybody identified it right there. It's fxy equals e to the negative y squared. That's your capping surface. So we're just trying to figure out the base of our solid right now because that's super important because that operates as your region of integration. So here you're going to graph x equals 0, and then the other planes, y equals 2x, that's a plane. So you guys know that's just going to be a plane that is diagonal, right? So it's going to look like something like that. There's y equals 2x, and then y equals 2. Oh, that's just a horizontal line, but in 3D it would be a plane. Okay, now what do I shade in? What's my R, my region of integration? And for this case, it's the base of my solid. You guys see what's to be shaded in there?
That triangle.
So this is the base of our solid. And it's understood that this, for this example, it's the R. It's the region of integration. So when we set up and evaluate the iterated integral representing the volume of the solid, if I just do the generic version, I'm going to do a double integral over the region R, where R is the shaded region here, and then the capping surface, and then dA. dA is the area element. for rectangular, which is either dy dx or dx dy, depending on your favorite choice of integration. So if I first choose my favorite choice of integration, just because, you know, I like thinking in terms of x. That's just how I roll. If I iterate this, I'm not going to iterate it yet because I want you to see a problem right off the bat before I start putting the limits here. I mean, I could put the limits here. It's actually going to be 0 to 1. Well, heck, why don't we just do it? Let's iterate it. And then I'll show you why we're going to get stuck. So let's do the outer limits first, because we know that's the easier one to iterate because it has to be pure numbers. So what number to what number is x doing on this base of our solid?
0 to 1.
Yeah.
Yeah, good. Do you see that this actually has the coordinates 1, 2, this point here? So if you look down here, yeah, x is going to go from 0 to 1 for this little triangular region. Now, what's y doing? Don't tell me 0 to 2. I'll get so mad at you. It's not going to be a constant to a constant. Remember that all pure constant limits for a double integral means your region of integration is a rectangle. And I hope you see that this ain't no rectangle. It's a triangle. Now, one of the limits might be constant, but certainly not both. If I stick my little man in here, here he is, he's vertical. I hope you can see that his head, no matter where I place my little man, is always going to be constant because he's going to be touching that horizontal line. So that upper limit is a constant, and that upper limit is y equals what?
2.
2. Now his feet are going to vary, but they're standing on this diagonal line, which we already know the equation. It's y equals 2x. Good. Now what? Now, why do I claim that this integral, even though I set it up, is going to receive you 0 credit? But you said you'd give us credit for setting up a double integral. Not this time. I want you to see that this is not integrable. And there are some integrals that aren't integral. We talked about that last time. In fact, some of you have had me for Calc 2, and we talked about, you know, you have to replace it with a power series if you want to sort of get an approximation of the integral. And I claim that e to the negative y squared dy is not integrable. I don't care. Well, you sub. Well, good luck. It's not going to work. It's not integrable. You're stuck. Now what? Anytime you run into that kind of brick wall, now that you're in Calc 3, instead of saying, no solutions, or like a Calc 2 person, okay, now we got to do this series, power series. You're not going to do that. No power series here. You're going to switch the order of integration. So that tells you to switch the order of integration because, folks, look, when I switch this order of integration, so here I am, the integrand stays the same. All I'm doing is I'm switching the order. It's got to be dx dy. I hope you can see we have to iterate it in a moment. But if I integrate that with respect to x, that innermost integral first now, when I integrate with respect to x, y is held constant. Hey, this is integrable now. Since y is held constant, e to the negative y squared just looks like some constant, like the number 2. And we can certainly integrate 2 with respect to x, right? So that's the motivation. Isn't that cool?
Yeah.
I mean, you should be saying like cool beans right now.
Or awesome sauce.
Or awesome sauce. One of the two. Or cool beans with some awesome sauce poured on top.
Cheese.
Cheese. I mean, this is like amazing. That's what makes this so much fun. When you couldn't integrate and you're like, now I can't. Okay, now we got to iterate. So this is the harder part because dx dy is the order of integration. It's like, it's, you know, it's like you got to think in functions of y. But let's do the easy one first. So the outermost integral is with respect to y, and that gets to be pure number to a pure number. So now look at this region of integration here. What pure number to what pure number is y doing? Tell me.
0 to 2.
Yeah, 0 to 2. So you go, okay, 0 to 2, we got the pure numbers. Woohoo! Now the hard part. Okay, what's x doing? And don't tell me 0 to 1. No, don't do that. I'm going to put a little man in there. But now that I'm choosing the horizontally simple order of integration, the little man has to be drawn sideways, where his head is pointing to the right and his feet are pointing to the left. Okay, there he is. He's lying down. And by the way, don't put it the reverse where his head's pointing to the left and feet to the right. You're going to get it wrong and you're going to choke. So let's do the lower limit first, because I claim no matter where I arbitrarily place this little man in this region, his feet will still be touching that same lower limit, which is just the y-axis, but that has the equation x equals what?
0.
Yeah. Now what? Well, his head is touching the diagonal line. So do I put 2x here since that's the equation y equals 2x?
No,
No.
No, good. Why not? Why is that not okay?
it's not in
Yeah.
terms of y.
Yeah, you don't want to have your limits matching the same as the variable of integration. That's a no-no. That's violating one of the rules and regs of the iterating double integrals. So what are you going to put there instead?
Y over 2.
Okay, how did you know that?
I just got in terms of y from the line equation.
Over here, I'm doing some scratch. And yeah, you need to solve this equation, the line equation for x, so it's written as a function of y. Now you can go like that, y over 2. And now we're good to go. Let's do this integral. So if I integrate e to the negative y squared with respect to x, totally doable. E to the negative y squared just looks like some constant multiple times x, and x is going to get evaluated between his limits, lower limit 0, upper limit y over 2. Fine. So now what? Well, then this is going to be y over 2 minus 0, but, the 0 is there. So then what do we have? We now have e to the negative y squared times y over 2 dy, and we still have the limits there. So now I hope everybody can see that this is integrable because we can use the exponential rule, which says integral of e to the u du is e to the u, but tell me who the u and the du are. Otherwise, I will not give you credit. Because a lot of the apps and websites out there don't identify u and du, and that's how I can tell you're cheating. So put the u and the du. So what is the u for this one?
Negative y squared
And then du?
minus 2y dy.
Okay, good news and bad news. We do have a y dy already in the integrand, but I have a 1/2, but I don't want a 1/2. I need a -2. The 1/2 I'm just going to pull out front here. So I'm going to put a -2 in there, provided I multiply the front by -1/2. So what do we have in the front now? We have this 2, which is a 1/2, and then we also have the -1/2 because of the exponential rule. And so now this looks like e to the u du right here, the integral of, and so now we're going to have e to the u, and then you're going to put your u back in before you evaluated the limits. And I had a student ask me if it's okay to redo the limits for double integrals, and I really don't want you changing the limits. Just back substitute for me, please, every time, and evaluate at the given limits. Be easier for me to grade and less work for you to show. Just take a few.
Uh-oh.
Did she cry?
I was really hoping it wasn't me, but now I'm really sad that it's her.
Looks like my internet died. I'm back. Sorry. It's always something. You know what? Friday seems to be internet death day for my computer. I don't know if it's just a thing or Cox likes to maybe take a break on Fridays. Good Lord. Weird. Okay, so where did I get cut off here?
Yeah, we're integrating.
We're integrating. Okay, are you guys okay with where I am right now after doing the exponential rule?
Sure, go ahead.
Yes.
Sure, keep going. Okay, so now it's just a matter of, I'm going to pull the -1/4 out because it's bothering me. I'm going to plug in that upper limit and then minus the lower limit, and I get this lovely number, -1/4 times e to the -4 minus 1. And believe it or not, that is a positive number, and you want to check because it's supposed to represent volume. If you want, I will accept +1/4 if you distribute the negative and rewrite it. 1 minus e to the -4. Both are fine. They're the same thing. And the approximate answer, if you whip out a calculator and punch it up, is, well, I don't have it. Sorry, I thought I did. Well, you'll go use your graphing calculator And I claim it is a positive result, thank goodness, because, you know, we're representing volume here. So then, you know, cubic units. Okay, questions?
I just want to make absolutely certain. So the limits don't need to be rewritten in terms of U.
Well, yeah, I want you to leave the limits the way they were. Like some people like to redo their limits in terms of U instead of in this case, the Y. So just leave the limits.
Okay, I never thought to try it that way. I'll do that.
Do you see the limits were originally 0 to 2?
Right.
Already? You see this?
Yep.
With respect to Y, isn't it? Not U.
I just had to. Okay, yeah, I've always had the habit of rewriting the limits for the new differential. All right.
No, but I need you to back substitute for U and get back to the Y's.
Got it.
That's how I roll. Okay.
For your integral, the very last step that you took before you were solving for your limits, so where it says 1/2 times -1/2 and then the integral
Right here?
right there.
Okay.
So would it be all right if I was to put EU times du, but then when I finally would solve for the limits, then I just back substitute, but inside the integral I have EU times du.
Well, I have that here, right? And then I do the intermediate step. And then I back substitute, and then I evaluated the limits. I'd really like you to do it the way I'm doing it here. You got this, then you show me this, then you show me back substituting in that order.
Okay.
I know I'm going to be very specific, and part of it is because I have a grader helping me, and when she and I are grading your papers, well, not real paper, we like to see the steps because I have a rubric that is being followed. And if you start skipping around steps and doing it differently, it makes it very difficult for us. It took me over 10 hours to grade your midterms. It's a labor of love. And so if you make it more difficult for me and my grader also, you know, we have to like figure out, oh, okay, you know, oh, what are they doing here? Oh, then we're less likely to give you partial credit if it's wrong, okay? So just try to be clean about it. I think this is pretty conventional, the way we're doing it here. So I'm just asking you to be in convention. I think it's fair.
Cool.
Yeah, I'm not doing anything out of the ordinary that you haven't seen already, other than it's brand new double integrals, right? Okay, now we're going to do a really weird problem that I used to not do in my lectures, but I'm going to do it just to mess with your head. It's a classic problem that's in more than one calculus book, so let's consider it. So I'll just set it up. It's going to be a very strange solid, and the volume that we're trying to find is actually in all 8 octants. Like it's a solid that's going to be all over the place, but it's going to be really hard for us to do limits. But what we're going to do is we're going to go, you know what, all the 8 octants and the solid that's sort of bleeding over into all the octants, it's got so much symmetry that if we just focus our eyeballs on just the first octant portion of this really wacky solid, because of symmetry, we'll just figure out that volume and then we'll multiply that result by 8 because the solid has the same volumes in all the other 7 octants. And that's legit if you have this kind of symmetry that's going on in this problem. Now, you can't always do that because if your solid is different looking portions in the different octants, then boy, forget it. You know, I mean, you can't even go, oh, I got symmetry, let me just go do this. So just to show you just some wacky, sorry, I can't. So I like to bring up my new calc here. Are you guys still there?
Yep.
We're here.
Yeah.
Just checking because I don't know what my internet's doing. So I'm having some technical problems. So like if I did some really weird solid, I mean, there's some really wacky stuff here that we could look at, but let's just see here. If I do, I don't even know what this looks like, but this will be fun. I got some really weird equations here. Let's see, sine x. Let's let's do a less than just for fun. Ooh, this will be fun. Let's see what this looks like. Okay, hit it. Oh, that's not a 3D. Sorry, my bad. Let me redo. I was looking at a 2D thing here. Let's just do this one. Here's a really wacky looking surface here. Whoa, okay. So I hope you can see this is an interesting surface. And it might have some symmetry to it, but not every octant might have the same look to it. So you have to kind of be careful when you make the call that, oh, it's got symmetry everywhere, because it, you know, as a capping surface, it might not. Because it looks like it's above, the XY plane is usually the arrows. So in one area here, it's above the XY plane, but down here it dips below. So there's not symmetry going on here. So you got to be careful when you're doing some of these problems that you don't just say, oh yeah, I've got symmetry, and you really don't. And that could be like a true false question. Okay, right there. I'm just saying. Okay, so now if I were to do what we're doing here, look at the example 13. Take a look. What do you think is going to be the capping surface there? This is a hard problem.
You say example 13?
You mean 14?
14, sorry, I meant 14. What is the capping surface? You've got x squared plus y squared equals 9, and y squared plus z squared equals 9.
I don't know.
Okay, remember
to-
what I said about z being sort of your key, your fxy?
Yes.
Y squared plus z squared
Z
equals 9.
equals 9. Is going to be
Yeah,
our
what
capping
you're
surface.
going to need to do is you're going to need to solve this equation for z, and you're actually going to get two versions of it. You're going to get plus or minus the square root of 9 minus y squared. So there's like an upper and a lower. Do you guys recognize this as a cylindrical surface from like 2 months ago?
Yeah.
Yep, it's
Does
missing
everybody
X.
remember this? And you should, because I claim everybody in this room, if I gave a pop quiz, which I'm not, don't worry, you should be able to actually sketch that 3D solid. So what do I mean? Well, in the YZ plane, you first draw the generating curve, which is a circle centered at the origin of radius 3, and then you whoosh it in the direction of the missing variable, right? Hello?
Right, correct.
Yeah.
So you whoosh it in the direction of X, and you do get a cylinder, okay? So I hope you can see the upper portion of our capping surface is sort of the upper can. This can is sort of lying on its side. And the negative square root of 9 minus y squared would be the underbelly, you know, the underbelly part of this can. You see that? Now, what about this other equation they're giving us? Well, folks, this is also a cylindrical surface. Come on now. Really? Yes. Yes. If you would graph that generating curve in the XY plane, yeah, I like whoosh too. Thanks, Nick. And in the XY plane, that's another circle centered at the origin of radius 3, okay? And you're going to whoosh that puppy, here's the XY plane, in the direction of the missing variable, and that's the z-axis. So you have an upright Coke can. Well, what the hell? Which one is our capping surface? This sideways guy is our capping surface. This upright can is just helping us to get the region down in the XY plane. It's going to be the region of integration. So the region of integration here is, I'm trying to draw a circle of radius 3, and I'm blowing it, sorry. Circle of radius 3 centered at the origin. This is the x squared plus y squared equals 9. This is our region of integration. It's not really the base of the solid, because the solid doesn't really have a base in that kind of sense. So this is where I want to go back to new calc. First, I'll graph the y squared plus z squared equals 9. That's basically our capping surface. Not satisfied in the coordinate regions given. What? So it doesn't want to graph this either. That's unfortunate. Let's go to GeoGebra and see if it's going to be happier. Interesting. Everybody's saying, nope, I don't want to graph that. Not my job. Okay. Right on. Let's see if this guy is going to let us do it. I don't know. Oh my goodness. Okay, there. Aha. Sideways can. All right. Now, let's do the other can, which is vertical. That's the x squared plus y squared equals 9. Woo! And that, so the hard part now is imagining where these guys intersect and what you're looking at. So the solid bleeds over into all 7 octants. So if we just focus on the first octant portion only and then multiply it by 8 to acknowledge the symmetry, we'll be good to go. So this is a hard problem. I'm not putting something this hard on the quiz, okay? Before you start wigging out, relax. I just want you to see kind of a hard problem here. So, you know, here we go. If you look at this first octant portion here, you're like, oh man, you got sort of this capping surface only. And then down here is going to be like that. That's kind of what's going on there. That's your solid. You're trying to find the, what AB the midterm? I have no idea what you're talking about. Isaiah?
He says, what if you put that hard of a problem on the midterm?
No. No. Look, I don't know. Maybe you still don't know me, even though we've been together for 2 months, Isaiah. I thought we were family. But if you get my way of doing midterm problems, the midterm problems are pretty much in the same challenge level as your quizzes. Yeah. In fact, I put some of the quizzes problems on the midterm. I don't put something like that's harder. Yeah.
Yeah.
No?
I figured. I just want to not have nightmares about this.
Oh, okay. All right. Well, we want to prevent nightmares because that's terrible. So here's my plan. 8 multiplied by the volume in the first octant is going to get us where we need to be. So the volume is going to be 8 times a double integral. And the capping surface is going to be positive square root of 9 minus y squared. And if we choose dy dx, and we look at what's going on in the xy plane and just look at the first octant version, if x is going from a pure number to a pure number, and then a little man here, this equation is y equals square root of 9 minus x squared. So the limits for y would look like this. And I hope that everybody sees that if we were going to integrate that, you would need trig sub. But remember, I promised you in this class, I'm never going to give you an integral requiring trig sub. And that's my promise to you, okay? So if any time you're doing your homework or a quiz or a midterm or the final and you went, oh, I have to do trig sub, Professor Rasky lied to me. Stop yourself. That's not true. Don't doubt me here, people. You need to switch the order of integration. Because you're not supposed to be doing any trig sub in my class. I don't want you to have to work that hard. Now, my Calc 2, they are going to be doing trig sub because, you know, that's a Calc 2 thing. So how do we do that? We'll still have the 8. So I'm going to have my order be dx dy instead. So I claim it's going to be a really easy problem. This is the whole point of this. I want you to see. So y is going from a pure number to a pure number. And if I turn my little man over to the side now, and my eraser is not working, okay, that's fine. My little man is going to be sideways like this. So the lower limit for x is just the y-axis, which is x equals 0. And then if I solve that circle equation for x, so now it's a function of y, I'll have x equals the square root of 9 minus y squared. So that's the upper limit on x. Now this is integrable, no trig sub, because we're integrating with respect to x, and the square root of 9 minus y squared just looks like a constant multiple to me. So good news, good news. Just have it go along for the ride, and then have it x, and then evaluate at the limits. And then I hope you can see that I'm going to just multiply the square root of 9 minus y squared times the square root of 9 minus y squared. Well, what's that, people? Come on.
9 minus y squared.
And now I don't have any hard integration at all. I'm just going to go, oh, this is easy to integrate, for any calculus 1 student, and 0 to 3, and I get 144 cubic units for this solid, okay? And so what was the point of that? The point is sometimes these solids are really hard to imagine, but always try to get your capping surface. The one that you'll select is the one that's got a Z in it, and you're going to want to solve that for Z to get your capping surface, okay? That's the point. So when you get hit by a lot of equations, don't just like, I don't know where to begin. That all looks like capping surfaces to me. It'll be pretty obvious. Okay, now check out example 15. It's another flavor for you. This one I've even given to my business calculus students, and it's hard. And yes, they do multiple integration in business calculus. I'm not kidding. Like, they do this. So if they can do it, you can do it. Well, they don't have trig, so they don't do trig type problems, but you should know how to do trig problems. Okay. So how about if you're doing the volume of a solid that's bounded by that equation and that equation? What's the region of integration? I hope you can see that you're going to solve for Z, and this essentially is your capping surface right there. Now, does this capping surface cut into the XY plane? Yes or no? I'll let you think on that for a moment. One of the sides of the solid is going to be given by this cylindrical surface. And if you just sketch this x minus y squared equals 0, if I rewrite it, it's x equals y squared. And that's just a horizontal parabola that kind of has this look to it, like that. Now, what I get students telling me when they do this problem, and this is a bit, even the business calculus people start telling me this, and I'm like, no. They went, oh yeah, this looks like the base of the solid goes on for infinity. That's it. There's the base of my solid. It's like, no, it doesn't go on for infinity. We're not doing one of those improper integral things. Well, what are we doing? Well, you got to be careful because this capping surface actually is a plane. It's a plane equation, and it actually does have a trace in the XY plane. So the trace in the XY plane is going to be found by setting Z equal to what?
0.
Mm-hmm. So when you set Z equal to 0 with this equation, you'll get X equals 2. And then that's a plane. And so when you sketch X equals 2 here, its trace in the XY plane, you get that. And so the base of the solid, which is our region of integration R, is this thing. Now, is that only in the first octant? No. So this is the time when you have to see that it's not always relegated to just first octant solids. So that's our region R of integration. And so your volume is going to be a double integral. You're going to put your capping surface there in the integrand. I'm going to choose my favorite order of integration, but I'm going to tell you right now, it's going to be harsh. Why? Because X will go from 0 to 2, no doubt. But if you try to iterate this with the order of integration that I have, your little man's head and feet are on the horizontal parabola. Well, what does that mean? Well, your horizontal parabola, if you solve it for y, it has y could be either plus or minus square root of x, which is fine. You can iterate it like this. This is legit, okay? And this will work. Go for it. And it's not too hard to integrate. But usually when I have regions like that, it's typically easier to iterate it using the other order of integration. I'm just saying, you don't have to. So here, what is y doing though? This is a little bit trickier. And you're going to have to figure out these intersection points. So when x is equal to 2 and 2 is equal to y squared, because x is equal to y squared. Yeah. So when you solve for y, you get plus or minus the square root of 2. So the pure number to pure number that y is doing is negative square root of 2 to positive square root of 2. That's what the y coordinates of those intersection points are. And then what's x doing? Well, if you draw your little man sideways, he's like this, his head is the upper limit, which is a constant, it's 2, and his feet are on the horizontal parabola, which has x equals y squared is the equation. So this is pretty easy to integrate. So let's go ahead and do it. And it can be a little tedious, and that's why I left a lot of room. It's like, oh, this looks like it's going to be pretty easy. And it is. But you have to be very careful. And sometimes students want to get stuff done in a hurry, and then they choke when it's the easier part. So here, you're going to first substitute your upper limit. And then you substitute your lower limit. And you have to be careful here because you have y squared squared there. And so this is what? 4 minus 2, which is 2. And then if you distribute the negative here, your integral, and now it's just a Calc 1 problem, is that. And then you're going to integrate this with respect to y. I'll let you finish out the rest. And the limits are a little bit funky because of the square roots, but you should get 32 square root of 2/15 cubic units. And we're done. Okay. So what was the flavor of this one? Why did I give it? Because it usually throws people for a loop. They can't figure out the base of the solid because they think it's going on for infinity, when in fact it isn't, because this particular capping surface cuts into the XY plane and stops the base of the solid from being an infinity base. So you have to think a little bit when your capping surface does cut into your XY plane. That flavor is different from the others. And it's not just the first octave. So here, types of math used in Calc 3, a lot of algebra. Sometimes that gets people. Okay, so anybody have any questions regarding anything that we looked at just now?
When
I'm good. Go ahead.
what was the indicator for you finding the XY trace? The fact that it looked like it went on to infinity when you
That's one of
grabbed-
them. That's one of them. And when you set z equal to 0 in the equation that has a capping surface in it,
Mhm.
it actually does cut through the XY plane because you get x equals 2, and that can be graphed in the XY plane.
Okay.
The other flag, if you will, that's saying, hey. And of course, practice. Like practicing a lot of these kinds of problems. I just know because I've done so many of them. Yeah, I can tell you that, you know, each of these ones that I'm putting here in my lecture kind of has a different flavor for, that you can get. And of course, I can't do all the flavors. That's why what the homework's for. You know, I want you to go do the homework. Like I haven't done yet something that requires the arctan rule, have I? Oh yeah, I did. I think I did one before. Did we do one that with an improper integral? So on the quiz, just so you know, on Sunday, expect one of everything. Like I'm going to give you something with integration by parts. Yeah. A double integral with IVP. Yeah. You'll have an arctan rule. You're going to have an exponential rule. You'll probably have a log rule. You'll probably have an easy one with just polynomials also. You know, that's a given. But know how to do other things too. Like, you know, if I ask you, you know, how to take the integral of sine, you know how to do sines, cosines. What are some other ones? Do you know what the integral of tangent is? Tangent u du? That might be something worth looking up. Keep that handy as far as your formula sheet. You know, all those trig things, right? Hello?
Yeah, of course.
You know, all the stuff that you learn in Calc 1 and Calc 2, I mean, if you forgot all that, like have a formula sheet ready at your side while you're taking your quiz. Just be ready, you know, and do your homework first because you'll have seen it. You'll go, okay, I saw that one, or something like. So no surprises. You should do okay if you know what you're doing. It's all integration. So it's not going to be tricky in that, oh, there's something other than integration. Now, on the quiz, what's the quiz going to be on? It's going to be 16.1, 16.2, and Lagrange multipliers, which is 15.8. I haven't quizzed you on that yet. So, but a lot of you love Lagrange, don't you? Isn't it Lagrange wonderful?
Yes.
I think so.
Think so? Okay, well, then do some Lagrange because it's awesome. You'll have a couple of those. You guys are buds, huh, Isaiah? Okay, cool. All right. You ready for polar?
Let's do it.
Nice stuff, people. Polar. I know you forgot it. It's okay. Don't worry. I'll start you from scratch. I know you forgot everything from Calc 2, right? But not your IBP. You can forget about trig sub. I'm okay with that. Go for it. Go ahead and forget trig sub. Forget that. Now, don't forget partial fraction decomposition, though. We're not going to do it in this class, I promise, but you'll see it in differential equations, and so you don't want to forget that. It's important, okay? So how we doing, everybody? Are you still with me?
I'm here. I'm awake.
Mm-hmm. I'm looking at all the peeps here that are in the room. Yeah. Interesting. Okay. All right. So we're going to look at polar. Where is it? Not Calc 2. You want Calc 3. So polar, what is polar? I mean, who cares? Like, I don't want to do polar again. It was just dumb. You know, who cares? And the reason why you want polar for us, just to give you the motivation to study it, it's going to turn out that we'll end up with a double integral representing something. And you'll notice that even if you try switching the order of integration, it's still not integrable, whether you have the dy dx order or the dx dy. Either way, you can't integrate it. It's like, oh man, what do I do? And it turns out if you convert everything to polar, and we did that kind of with limits at one point, it's integrable. And you're like, oh, sweet. Okay, now I can integrate. And that's the motivation. Okay. So I'll write this down, what I just said. Some integrals are much easier to evaluate in polar form. And this is going to be especially, I can't spell form. This is going to be especially true for your regions of integration being polar regions. For R, the region of integration. Region of integration, sorry, that are the following candidates: circles, petal curves. You guys remember those petal curves from Calc 2? You graph them and they look like, something like that.
It's pretty.
Those curves, yeah, those cardioids. What's a cardioid? Oh, it kind of looks like butt cheeks. And then integrands with x squared plus y squareds in it. Integrands that have an x squared plus y squared in it. So these are all good candidates for converting the whole shebangy to polar coordinates. Okay? So polar coordinates are cool. So let's just do a quick review because I imagine that you may have forgotten what the heck and how to do. All polar coordinates are, it's a different way to represent 2D. Okay? So if this is your XY situation here, this is what we call the rectangular coordinate system. If you have a point here, P, that's represented by an ordered pair XY, then the exact same ordered pair over here in the polar coordinate system, the same point P, needs to be represented by an ordered pair, but the ordered pair has R and theta in it. Oh, whoa, how do you get from one system to the other? And that's what it's pretty easy actually. If somebody gives you the X and the Y coordinates of a point, then it's going to turn out the R is like the hypotenuse, essentially. It's the distance of your point P to what we call the pole. And you can use the Pythagorean theorem. So X squared plus Y squared is equal to R squared. And that's one of the conversions formulas to get from here to here. Although the way I usually use it is R is replaced with square root of X squared plus Y squared. Technically, it would be plus or minus because R can be negative, but it's really messy when R is negative. So let's try to avoid those situations. On the other hand, what if you want to go what's theta? Oh, theta. So if you draw a theta there in your right triangle, and you already know what X and Y are, that's opposite and adjacent, tan theta is opposite over adjacent. And if you solve this for theta, you'll just basically have tangent inverse y over x. You have to be careful because just like when we studied 2D vectors, if your point is in the first or fourth quadrant, this theta works perfectly. But if your point is over here in quadrant 2 or quadrant 3, you're going to have to add 180 degrees to make that theta correct. Now, the reverse direction, again, it's just a trig situation. Using your right triangle, if somebody gave you the theta and the r and you needed to get your x and y, you would just go, well, sine of theta is opposite over hypotenuse. And when you solve this for y, you have one of the conversion formulas. And then similarly, if you use your cosine theta, and that's adjacent, which is the x leg there over your hypotenuse, solving this for x, you'll get x is r cos. So that's how you get from this polar back to rectangular. Okay, so before we do any actual examples of double integrals, let's just look at some regions that are best used for polar coordinates, okay? Take a look at this one, a quarter of a circle. That's a really nice region of integration that lends itself well to double integrals and polar. And you can even see it if I represent these using set notation. So in set notation, if I represented this quarter of a circle using x and y coordinates, it would look like this. The set of all ordered pairs, x, y, such that, and then you're inside of a circle of radius 2, so you'd go x squared plus y squared less than or equal to 2, and you're in the first quadrant, so x is greater than 0, y greater than 0. Got a lot of restrictions there. That shouldn't be a semicolon. That should be a comma, sorry. I've been doing too much code, so I do semicolons everywhere when I do Java, sorry. Yeah, my eraser doesn't work. Okay. So there we go. Wow, okay. But in polar, how do you describe this in polar? Nice. Your polar situation would be all the ordered pairs r and theta such that r goes between 0 and 2, and theta lies between, I'm doing semicolons again, sorry. Theta lies between 0 and pi half. So I want you to not think of r as being x or y axes. Because r, you can think of r as blooming outward, like it's sort of like concentric circles. And so for those of you who are like maybe still confused here about the r, let me talk about graph paper really quick. If you look at rectangular graph paper, it has a bunch of little squares on it, which makes sense because, in rectangular, it's all about mapping your ordered pair based on, your x coordinate, your y coordinate. If you look at polar graphing paper, it's a whole different look. You can actually buy this and it looks really cool. I'd say go to the bookstore, but they're closed right now. But polar graph paper, technically there's no x and y axes on in the polar coordinate system. I draw it here just to give us sort of the lay of the land, but technically that's not really there. What's there is you have not an origin, what's called the pole, which is like the 0, 0 point, and then you have concentric circles that are blooming outward, and then you have a bunch of rays that are directed outward from your pole, like this. So that way you can locate yourself in the world of polar. So if somebody tells me, the point 2 pi fourths, and I'm supposed to find the point 2 pi fourths here in the polar world. First, I would find the circle of radius 2, because that's where I'm going to be sitting on. So if I have all these circles here, let's say this is the circle that has radius 2, because it's 2 units away from the pole. And then pi 4, there is an axis in the world of polar, but it's like the positive x-axis only. That's called the polar axis. And pi fourths is the angle that we're making with the polar axis. So we're sitting here on the circle of radius 2 at pi fourths angle here. So there's the point P right there. And you can locate it using polar graph paper. Okay, so I want you to see that because sometimes I get people thinking of r as just being, that's the same as the x coordinate, and it's not. Okay, let's look at another region. that's considered a really good candidate for polar? A donut. Donuts are really great. You don't want to try to do a donut in rectangular because then you'll have to chop it up into 4 pieces in order to get all the double integrals iterated correctly, and it's a nightmare. So if you have a region of integration that ends up being a donut, use polar. So let's say this donut was concentric circles in between the radii 1 and 2. In rectangular coordinates, if I were to denote this in set notation here, it would look like this. X squared plus y squared is greater than or equal to 1, but less than or equal to 4. If I do this in polar, we're just talking about constants. So r is just a constant between 2 constants, 1 and 2, and theta is going to go around 1 full revolution, so 0 to 2 pi. You see how these are all constant limits? That's going to be key. Okay, let's do a quick penumbra of derivation here and then get to it. So I can finish off with at least one example before I kick you out of here. I don't even know if I'm going to have time for that. Well, we'll see. I want to start a little bit of polar. So the idea is you've got a portion of a circle or a portion of a donut right there, and that's called a polar sector. Cool. What about it? Well, R lies between some radius R1 and some other radius R2, and theta is in between theta 1 here and theta 2. So it lies in between. Great. Now what? Well, let's just look at a polar sector. Here's a polar sector, a pizza slice. You guys know how to get area of a pizza slice? I know you know how to get the area of a whole circle. Does anybody know how to, the formula for a pizza slice? I'll open it up. Pizza, anybody? Yeah. If we were face to face, I'd scare everybody right now. Okay, everybody, take out a blank piece of paper. We're gonna have a pop quiz. What's the area of a pizza slice? I'll give you one thing. Here's R. I'll give you that, and I'll tell you that the angle subtended by the pizza slice, you know, this angle here is some theta. Now, what's the area? Crickets, baby. Oh God, we're in trouble. Okay. Let's talk about the area of a full circle. Do you know what the area of a full circle is if I told you the radius? Okay. Well, that's the area. I think you're giving me the circumference. Area of a circle.
Sorry, pi r squared.
Pi r squared.
Yeah, okay, just checking. Okay, area of a circle is pi r squared. Everybody comfortable with that? Do you buy it? Now, that's the entire circle. That's the entire circle. What angle is subtended by an entire circle? Isn't it 2 pi? Okay. Hello?
Yep.
Yeah. What's going on?
Are you guys alive today or not?
Oh yeah, what's going on? Hey, Professor.
Okay, hey, I'm hanging out. So what I'm saying is this area, it took the angle, but it divided by 2 and then multiply it by r squared. That's exactly how you're going to get the area of a pizza slice. You'll take the angle that it's being subtended, divide it by 2, multiply it by the radius squared. Boom, there's your pizza slice area. Okay, so what? Well, that's going to help you because if you're trying to get the area of this portion, like if this is the whole pizza slice right here and I just want a portion of it right there, what's that area right there equal to? So that's what we're going to look at right now. And then while I'm doing that, I'm going to derive why the double integral of a polar double integral is the way it is. So if you look at, let's look at a pizza slice again. Let's say that this outer radius is R2. And let's say we have an inside pizza slice here with, and I'll do a different color here, what the hell, red, inside pizza slice, where his radius is R1. And I want this area here. What is that area equal to? I claim it's the area of the outer pizza slice with radius 2 minus, because I'm cutting away, I'm like chopping it out, minus the area of the inside or inner pizza slice that has a radius of R1. Would you buy that?
Yeah.
Yes.
Does it look legit? It is. Okay, so then what? Well, knowing now that you know what the area of a pizza slice is, you're going to go 1/2 the angle, and let's just say this angle here is delta theta, which is the same for both pizza slices. So you're going to go delta theta is going to be like a theta 2 minus a theta 1. And so you're going to go, all right, the outer pizza slice has 1/2 the radius squared times delta theta minus the inner pizza slice 1/2 the smaller radius R1 getting squared times the delta theta. Do you see a common factor here? You mind if I pull the common factor out? 1/2 and we've got the delta theta. And inside I have R2 getting squared minus R1 getting squared. Doesn't this look like a difference of squares to you?
Right.
It is. Well, yeah, so what? Well, I claim it factors. Well, okay, use a little bit of your algebra know-how. Great. So I think it factors is the sum and then the difference. Okay, so what? Okay, we're getting there. Don't worry. Take a look at this baby. Doesn't this look like an average to you? An average of what?
Of the radii.
Of the radii. Bingo dingo. Very good. And then this is the difference of the radii. Yeah, so what? So we're going to do 2 renamings right now. 2 renamings. Try to follow me. The difference of the radii, I'm just going to call delta R, because that's typical of what mathematicians do when they have a difference. They go delta, whatever. Delta represents a difference. Okay. Then this average, this 1/2 of the sum of the 2 radii, I'm going to replace it. Now, some books call it R sub I. That represents average. Other books use statistical notation where they use R bar. If you've taken a stats class, you know the X bar is the average of the data. I like R bar myself, but it doesn't really matter, okay? What matters is it's something. It's an R sitting there. Okay, now what? Okay, what we're trying to say is that the delta A sub I, this area of this polar sector that I'm trying to find, that's a delta A sub I of a whole bunch of little polar sectors, is going to be some difference of theta, some difference of the radii, and then that average radii. And so if you're trying to use a double integral in polar to represent the volume of a solid, you're going to have a capping surface, fxy, but you're going to replace the x and y with the polar conversion formulas. So you'll replace x with r cos and y with r sine. So there's your capping surface, basically the height of your solid. You're going to multiply by your delta A sub I, that's your area element, and then put it all together. They first do a Riemann sum, and then they take the limit of the Riemann sum as the partition gets firmed up. And so then your double integral looks like this. Okay, yeah, so what? There it is. Okay, so why do I have a picture of a parrot with a pirate costume on?
It's
And he's
cute.
saying,
Birthday party.
what?
He's having a birthday.
He's having a birthday? No, that was last week. Yeah, Zeke had a birthday. No, this
Zeke
isn't
joined up
Zeke.
with the Somalian pirates.
That's a good one. No, he did not. Sorry. Here's what I want you to notice. You know how when we did the area element for rectangular, the delta A ended up being delta Y, delta X, or basically dA could be dy, dx. Well, dA in polar doesn't look like just dr, d theta. It ends up being r dr, d theta. There's an extra r in there. R. Get it?
Yeah.
Be a pirate. Where'd the R come from? Okay, come on. I just did the derivation for you. Don't be asking me that. The extra R with this whole derivation came into the being here with that average radii that came in there, that R bar. There's your R. Okay, so here's your theorem, and then we'll do a problem, and then I'll kick you out of here. Let's see how fast we can do this. It'll be quick, don't worry. So here's the big old theorem. If you're going to use change of variables to polar, and you're going to want to because it's sweet, You're going to have some R, that's your region of integration. And, here's your conversion formulas, okay? And then your R is going to go from some G1 of theta to some other function G2 of theta. Your theta is going to go from, like 0 to pi halves or whatever. It goes from some angle to another angle. You want to stick to being within 2 pi, otherwise things get a little bit much. So don't try to wrap around. And, oh, thanks. Cool. And then what you're able to do is you're able to go, okay, here's my rectangular coordinates integral. And I'm going to convert it to a polar. So you're going to have your outermost integral is typically with respect to theta. So he'll go from some angle alpha to some other angle beta, pure numbers. And then you're going to have your inner integral be with respect to r, and it'll go from like G1 of theta to G2 of theta, but it can also be pure numbers. And then you're going to have your capping surface where you convert all your x's and y's and replace the x's with r cos and replace the y's with r sine. But what am I missing here? Be a pirate?
R.
R! R! Goes in there. I know I'm being ridiculous, but you will thank me later because it will save you from blowing it. Okay, so be a pirate. Let's do a quick example. This is really fun. It's really easy, and then we're out of here. Okay, use polar coordinates to evaluate this integral. Well, why do we need to? Why don't polar sucks? Well, do you want to do trig sub? Because I sure don't. If you like trig sub, go integrate that using trig sub and get back to me in 50 years. Okay, forget that. I don't want to. Like, please don't make me. This is way easier to do in polar. Let's sketch the region of integration first. So if you use the Raschke no-fault way to do this, you look at the limits and you make those equations, x equals 2, x equals -2 are two things I'm going to have to graph. You look at the limits on the innermost integral, which have to do with the variable y. So you're going to need to graph y equals square root of 4 minus x squared and y equals 0. So if I graph all 4 of those graphs, and this is just the upper half of a circle, it's a semicircle. Well, that's a pretty sad semicircle. But I hope you can see that our region of integration is a semicircle. Beautiful. Nice. And it's a perfect candidate for converting to polar. Thank God. So now what? Convert everything to polar. So what is r and what is theta doing on this region of integration? You want to do that because you're going to have to iterate your double integral and you need to know the limits. And the good news is I claim everybody is pure numbers for this polar. So theta is going from what angle all the way to what angle? Should be pretty obvious.
0 to pi.
0 to pi. Very good. Nice. And then what is r doing? Please do not say -2 to 2. Remember, r blooms outward. It kind of starts here at the 0 and then blooms out.
0 to 2.
Very good. 0 to 2. Beautiful. So that's nice because it's going to make this sweet to integrate. Nice. So what am I saying? When I convert this puppy, this integral becomes this brand new integral. I've got 0 to pi. I've got 0 to 2. R dr d theta. That's what I replaced the dy dx with. R dr d theta. And then how do I convert that capping surface? Well, I don't know if this represents a volume, but it could. How do I convert that to polar? Now remember, you could replace the x and y with r cos and r sine and clean it up. But I claim, hold on, this one's a little easier because x squared plus y squared is the same as what?
R squared.
R squared. If you go back to my original little conversion thing here, remember, if you see an x squared plus y squared in your integrand, yeah, if you want, go ahead and do, r cos r sine. But after you factor out the r squared, cos squared plus sine squared is going to add up to 1. So you don't need to do all that. So that's just going to be r squared. But this is being raised to the 3/2 power. So now what? Using exponent laws, what does that end up being? R to the what?
R cubed.
So now you have r cubed times r. Well, please write that as a single power of r before you integrate. And then integrate. Well, r to the 4th has an integral that's r to the 5th over 5. And when I evaluate that between 0 and 2, I think I'm going to get 32/5. Oh, and I'll just pull it out in front oops, not 32 pi yet. And then I'm going to integrate between 0 and pi there. And what's still left in my integrand? Just a 1, essentially, because you're just doing the integral of 1 with respect to theta. But that's going to be theta. And then you evaluate your theta between your limits. And I'm going to get pi minus 0, but that is just going to be pi. And so my final answer for this lovely polar coordinates problem is 32 pi. Have a great weekend. Maybe I'll see you in office hours today. You're welcome to come. Otherwise, bye. If you want to stay for 5 minutes, that'd be great. Otherwise, okay.
Professor, can you scroll back up to the main equation, the theorem?
Yes. Okay, Emily, I see what you're talking about. As long as you're using your same name, it won't show up weird. It just goes by your name. Okay. So tell me when to stop.
Oh, too far. Back down, back down.
Sorry.
I just passed the.
Right here.
Yeah, right.
Be a pirate.
So you're doing a see you during office hours, Professor.
Okay, I'll look forward to it, Nick.